Okay, hello. My name is Gabriel, and this is a mini project I am doing as a post O-level plans. I'm a 16-year-old and a secondary 4 student who just finished his biology O-levels. And as a result of all my hard papers being finished, I decided to have this mini project of doing mathematics and going into a bit of JC math, even though I'm a Sec 4, and literally revising the whole AMF syllabus just because it's my favorite subject. So if you're wondering why I was looking down instead of in the camera, and I'm not going to look in the camera that much because I need to remind myself, the reason is because my computer audio is terrible, and as a result I need to record on my phone, and I need to edit in the volume later and silence the computer volume because it is really terrible, but I will make do with what I have. So today I want to start off with I think 5 things I know about like post-secondary school math that I can easily explain to any math student, and I'm quite well versed with these 5 different post-math concepts. So I hope that you and I get to enjoy, and let's do some math together. Okay, so let's start off with the thing that uh, I haven't practiced in quite a while, but I still remember what it is. So this is what I want to start off with is inverse functions. So what are inverse functions? So firstly, let's start off with this thing. I bet many of you guys have been seeing this randomly throughout mathematic videos, and I'm really wondering what this is. So this is called f inverse of x, which is basically the inverse function of fx. But before I start on what an inverse function is, I have to start on defining what a function is. So what a function is that for every input, which you can call x, it will undergo a series of transformations based on something, and you will have an output which is fx. So for example, right, let's say your basic y equals to x, right? Let's say your input x is 1, then you will go through whatever the heck the transformation of the x's is, and then your resultant y will be 1. But one thing that separates a function from an equation is that a function can have many different inputs, but for each input only has one output. So what do I mean by that? Let's talk about maybe the most simple quadratic uh, function that is. So for every single x I substitute in, let's say x equals to 1, and y will be equal to 1, x equals to 2, y will be equal to 4, x equals to negative 2, y will also be equal to 4. Although I have 2 different values that give me the same output, I have 2 different inputs that give me the same output. The reason why this is a function is because no matter what input you put in, you will only get one output. So for example of something that is not a function, a circle is not a function. A circle is an equation. For people who are watching this and do not understand what this equation is, this is the standard form of a circle. And basically, it's an extension of the Pythagorean theorem, but I will not be going that into today because I'm making this current video with respect to students who have finished the 2020 A-Math paper or take A-Math as an O-level student. However, I will be going through circles because it is in the A-Math syllabus. But for now, so this is not a function because maybe I should give a worked example. It's 25. So let's say x is 1, right? If x is 1, this will be the resultant y. It will be y squared minus 2y. minus 24. And using your quadratic formula, you realize that you have two y values. However, as I said just now, a function is defined that for every input there is only one output. However, here you have two outputs as a result of this. Therefore, a circle equation is a very good example of something that is not a function. But what about your trigonometric functions? Even in the trigonometric functions, even in your exponential functions and your logarithmic functions, all of them, for every single input of x, will only give you one output of a y, which is why they are called trigonometric, exponential, and logarithmic functions respectively. So what if you are a lazy man and want to find out whether something is a function? I want to introduce you to a concept called the straight line test. So firstly, to determine whether something is a function, it has to pass the straight line test, the vertical line test. So what the vertical line test is, if I draw a vertical line anywhere along the graph, if there is only one intersection, no matter where I draw the vertical line, it is a function. So now with that out of the way, let's move onwards to inverse functions. So what an inverse function is that it undoes a function in a sense that if you substitute the inverse function x into the original function or vice versa, or maybe let me just write it out. So let's say f inverse of x, you sub in fx equals to f of f inverse x equals to x. Maybe this seems confusing, so why don't you and I go step by step? So firstly, let's have an equation. Let's have a simple linear equation y equals to 2x. To solve plus 3, because I want to be mean to myself, to find the inverse function, what you first do is you swap the x and y's, and I am not kidding. So you swap x equals to 2y plus 3. After you swap the x and y's, you solve for the y. So 2y equals to x minus 3, y equals to half x minus 3. This will be the inverse function of this. So maybe let's call this fx equals to 2x plus 3. And this is f inverse of x, which equals to half x minus 3. So what did I mean just now? I'm sorry, I am a bit... So, let's substitute this into this. So, you know how your notation, like in polynomials, this means you sub 1 into in, right? So, instead of subbing a whole number, integer or a fraction, let's sub in another function, which I know this sounds stupid, but hear me out. So let's say f of f inverse x. You substitute every x value here with whatever this is. So this will give you 2 times half x minus 3 plus 3, which would evaluate to, oh gosh, x minus 3 plus 3, which will evaluate to x. Okay, interesting, right? What if we do the opposite? What if instead we do f inverse x? Fx. Let's sub in this into this. Half 2x plus 3 minus 3 equals to half 2x, which equals to x. As you realize, this is equals to this, which is equal to x. So what an inverse function actually is that you're reflecting the function across y equals to x, which sounds crazy. But that is the sort of like the definition of an inverse function. But in addition to the vertical line test that we established just now, there is another test to determine whether a function has an inverse function. So this test is called the horizontal line test. So let's use my y equals to x squared example again because I'm lazy. So using the horizontal line test, you realize that there will be two intersections. However, for a function to have an inverse function, the horizontal line should only cut the graph once. This means that y equals to x squared does not have an inverse function. So maybe let's try another thing. Let's try maybe like y equals to x plus 1, because I'm a lazy bum who can't think of any other graphs to do. So if we do the horizontal line test, you realize that no matter what, there will only be one intersection between y equals to x plus 1 and the horizontal lines. This means that y equals to x plus 1 has an inverse function, and not only that, since it passes the vertical line test, it also means that it's a function. And I just realized that this looks like a tic-tac-toe board. Ooh. Okay. So I'm going to give one last example, which I've saved on my Desmos. And hold on. Where is Desmos? Oh, okay. So let's have y equal to x plus 1 over x plus 3. And I'm going to cheat here and tell you that this is a function because I checked on Desmos. So, is it a function? Does it? Yeah, it is a function. So let's start off by swapping the x's and y's. So x equals to y plus 1 over y plus 3. So xy plus 3x equals to y plus 1. Move over the y, move over the 3x. You will get xy minus y equals to 1 minus 3x. Yx minus 1 equals to 1 minus 3x. Y equals to 1 minus 3x over x minus 1. And my math is terrible now after O levels. This will be the inverse function of this. So now let's kill ourselves and do crazy algebraic substitutions because we are madmen. So maybe f minus x will be equal to 1 minus 3x over x minus 1 plus 1 over 1 minus 3x x minus 1 plus 3. So, oh gosh. So 1 minus 3x plus x minus 1 over x minus 1 divided by 1 minus 3x plus 3x minus 3 over x minus 1, which will evaluate to 1 minus 1, which will get negative 2 over negative 2x over negative 2, which will give you x. So as you can see, this is the inverse function of this, and this is the inverse function of this. And that's all I'm going to do for inverse functions, because it actually is very powerful in calculus, especially in integration, because there are a lot of like formulas which I actually just discovered today, which I'm going to check out after I finish filming this. But I just spent 15 minutes rambling on about something I don't really comprehend. So yeah, let's move on with life. Okay, so let's now talk about my favorite thing, one of my favorite things in the world. One of my favorite things in the world is the definition of the derivative. So suppose we have a function fx. Assume that fx does not have an asymptote at x. So when x is x, Yeah, and this is going to get very confusing. So when x is x, fx will be fx. Does that make sense? So it's like saying when x is 1, fx will be f1. That is like the logic I'm using, except instead of having integers, we have variables. So let's have another point on the graph, the function called x plus h. So when x is x plus h, fx will be fx plus h. So let's like draw a line, like literally squiggly line. It may not be a function, but it can help you visualize this better. So let's have this point be x and fx, and then have another point be x plus h, fx plus h. So as you see, if I draw a line connecting these two, you realize that this is like, you can find the gradient of these lines by using fx plus h minus fx over x plus h over x. What happens if we move this point closer? Let's say like maybe around here, x plus h, fx plus h. You draw a line, oops, my bad. You draw a line, and this, you can find the gradient of this line also by doing fx plus h minus fx over x plus h minus x, which is your y2 minus y1 over x2 minus x1. So this is where the fun starts. Let's assume that this point, h, right, because the increase of this is h, let's assume h moves towards 0. And this is where the concept of this new concept, which I'm also not too familiar with, will be introduced to you. This is called the concept of the limit. So you know, in your exponential questions, they say that as x becomes very large, or when x becomes 0, what happens to the thing? So what when x becomes very large is, what happens of the limit of x as it approaches infinity? I know I suck at explaining this, but infinity is a very big number, but also not a number at the same time. I sound ridiculous, but yeah, never mind. I will not try to explain something I don't know. Anyways, so using our y2 minus y1 just now, let's have fx plus h minus fx over x plus h minus x. And we have a limit as h approaches 0, because just now you see, pretend the h is a moving point, right? And it goes closer and closer until fx plus h becomes fx. But here is where the problem starts. One way I see the limit is when, what does the graph equal to when it reaches a certain value. So let's say like x, the limit of x as it approaches 2 for maybe like what, 2x plus 1, your answer will be 5, because you can just directly substitute 2 into this. But in this case, as you can see, h is at the bottom, and you cannot directly substitute because your denominator can never be 0, because a lot of funky stuff happens if your denominator is 0. So this is the definition of your derivative. F prime x equals to the limit of h as it approaches 0 of fx plus h minus fx over h. So let's have some work examples now. So maybe let's have my good friend, let's start with maybe x. So let's say fx equals to x. So we all know that f prime x equals to 1 because of your power rule, in which your axn, you bring the n down, bring power down, power minus 1, right? But using the definition of this, let's do it together. So this is fx. Fx plus h will give you x plus h. Am I correct to say this? Let's now substitute these two values into here. So we have x plus h minus x over h. And then you realize something. You realize that your x's cancel out. And you're left with h over h. What does h over h equal to? Before you apply the limit, you solve any fractions or whatever. H over h equals to 1. And now you don't have to apply the limit at all, because the h cancels out and you get 1. So this is what you call the definition of your first derivative. Okay, so let me show you one more example, because I'm honestly too lazy to do all the expansion, because I've actually done like a cube expansion before, and I wanted to kill myself because of how much I had to write. And then like if you do like power 4, power 5, right, you have to use like binomial theorem to solve, and yeah, I'm not in the mood for that, so I'm sorry guys. So let's try x squared. So let's have fx equals to x squared. Alright, fx plus h equals to x plus h squared equals to x squared plus 2xh equals plus h squared. So now let's sub this into this. The limit of h as it approaches 0 of x squared plus 2xh plus h squared minus x squared over h equals to the limit as h approaches 0 of 2x plus h, because x's cancel out, divide by h, and voila, get here. So remember at the start of this explanation where I said that if you can substitute in the number, you can substitute it in. So let's substitute h equals to 0. That's why f prime of x of this is 2x. And it's the gradient, because this is how you find the gradient. Has your mind been blown? When I first learned this, I remember just screaming out of joy, because learning this actually helped me understand why I do differentiation. And the reason why I have less connection to integration than differentiation is because integration, I have not found like a kid's version that explains this as well for integration. So till then, I will probably make a YouTube video about it. But that's your definition of a derivative. And this works for literally anything. Actually, no, I will not be doing sine. I will not be doing trigo functions, because there are a lot of things that will cascade from there, and trigo functions requires like a bit of a higher level understanding of JC stuffs, which I want to teach you the stuff I'm comfortable with teaching. Even some JC stuff like your L'Hopital rule, I do not feel comfortable telling other people because I'm not too used to it. So that is the definition of a derivative. So yeah. Wow guys, this is moving fast. So now let's do the Maclaurin series, which is one of the things I find absolutely beautiful. So what is the Maclaurin series? The Maclaurin series is this thing called a Taylor series, which I have no idea what it is, where a lot of it, like your trigo functions and your exponential, your e power x, right, can be condensed into the form of x. So let me show you what I mean. So let's say sine x, right? The Maclaurin series for sine x is the summation from k equals to 0 to infinity of x minus 1 power k, x power 2k plus 1 over 2k plus 1 factorial. So remember how in statistics we learned that, like, okay lah, write it out, summation of this equals to, you add everything together, right? So this thing is called summation notation. So how are you supposed to read summation notation? Basically, this is the lowest of the k. this is the highest of the k, and these can only be integer values. So you substitute this in one by one and until you get something plausible. So let's substitute in together. So let's substitute k equals to 0. When k equals 0, negative 1 power 0 equals to 1. 2 power 2 times 0 plus 1 will give you x. Then this will be 1 factorial, which will give you 1. So let's now do the next one. When k equals to 1, since as I just established, everything has to be integer values, it will give you negative 1 to the power of 1 will give you minus 1. So this will be minus x to the power of 2 times 1 plus 1 will give you x power 3. Then if you substitute in 1 here, you will get 3 factorial. And you will realize that this thing, right, will alternate between minus and plus infinitely. So if I were to write out, it would be x power 9 over 9 factorial. So now let's do cos x. The Maclaurin series of cos x is the summation of k from 0 to infinity of negative 1 power k, x power 2k over 2k everything factorial, which will be, because I am lazy to do one by one, this. So if I were to write out the next one, it would be x power 8 over 8 factorial. Using the Maclaurin series, tell me why d dx of sine x equals to cos x, and likewise why d dx of cos x equals to negative sine x. Looking at this, think about it yourselves and you will be amazed. But in extension, this x can be any number. So let's say I want x to be 2x, cos 2x. The Maclaurin series of cos 2x will be just substitute in the 2x values. That's it. Let's move on to the last Maclaurin series that I think I'm comfortable with teaching because I'm too lazy to explain certain stuffs. The Maclaurin series of e power x equals to summation of k0 infinity of x power k over k factorial, which will be equal to, hold on, I'm a bit high, 1 plus x squared over 2 factorial plus x power 3 over 3 factorial plus x power 4 over 4 factorial, on and on and on. Using the Maclaurin series, tell me why d dx of e power x equals to e power x. I think you're smart enough to evaluate this. Yeah. Actually, no. In case you guys are dumber than you are, let me give you a work example. So d dx of e power x, you apply the d dx on both sides as equals to 0 plus 1 plus x over plus 2x over 2 factorial plus 3x over 3 factorial plus equals to 1 plus x plus 2x over 2 factorial and as I said, you can substitute in any x value and this will work out. If I have e power sine x, I can substitute sine 1 plus sine x squared over 2 factorial plus sine cubed over 3 factorial, etc, etc. I remember when I first learned about this, I was so impressed because I found it so amazing. And man, anyways, my bad, did not mean for my marker to drop. Let's talk about implicit. Actually, no, I am not going to talk about implicit differentiation because I have not found out a reason to why it works. So I shall skip and do integration by parts. In summary, what integration by parts is that it's a reversal of the product rule. So as established, let's say we have this f prime of f prime of x will be equal to g prime x hx plus gx h prime x. Am I right to say this? I hope that this is how you remember your product rule, because this notation will be very useful. So what integration by parts is, right, is that you're manipulating this to find, substitute this, when you integrate f prime x, you have to integrate the other side too. And this will result in gx hx equals to whatever this is. Am I not wrong to say this? Because the integral of f prime x equals to fx equals to gx hx. So what integration by parts is by breaking up your addition formula for integration, you are finding a way to make magic happen. So the definition of integration by parts is the integral of g prime x or minus hx equals to gx hx minus the integral of gx h prime x. Let's have a worked example. Let's say I want to find the integral of ln x. Haha, guess what? We are not taught this in our syllabus. But guess what? I will teach this to you. So let g prime x in this case be 1, because this is technically the integral of 1 times ln x. So g prime x equals to 1. hx equals to ln x. Am I right to say this? I hope I am. So gx will be equal to x. And of course, you don't have to care about the constants. And h prime x equals to 1 over x. So by using this definition, the integral of this dx, goes to gx, which is x, hx, which is ln x, minus the integral of gx h prime x, which will be gx h prime x, which will evaluate to the integral of 1 dx. And you'll realize that the integral of ln x dx equals to x ln x minus x plus c, where c is your arbitrary constant. So as you can see, if you differentiate this, you will get ln x plus 1 minus 1, and then you will get ln x. Pretty cool, right? So what about an example where you have to do integration by parts multiple times? Let's say I want to find the integral of x sine x. Okay? By integration by parts, I'll just use it now. Fx equals to sine x. Fx equals to x, g prime x equals to sine x. F prime x equals to 1, g equals to negative cosine x. Using your definition of definition of reverse. Am I doing it correctly? Yeah, I am, sorry. Equals to I think I might be wrong. I need to double check. X sine x. No, this should be plus c, I'm sorry. Okay, I'm correct. My bad. And I am sorry if it seems like this video is just me mindlessly rambling for 36 minutes, but I hope you sort of learned something new. And this is my first ever like math video, so I would appreciate if you guys gave me constructive criticism on how to improve like the video quality and all that. I mean, probably get a new camera if I get very invested in doing this. And I realized that this is a lot more tiring than I thought it would be, probably a lot more expensive because I need to invest into marketing. But I hope you enjoyed the video and learned something new. See you guys, man. Good night. It is 1:09 a.m. now, and my friends have a physics paper today. I wish you guys all the best. Oh shucks, this is still recording. Oh no, where are you?